I'm a PhD student at the Potsdam Institute for Climate Impact Research, and we'll talk a bit more concretely, pictorially about climate models, give a few examples of what we can do with them, what we can learn with them, and a few also an insight to like future projections and how it interacts with the policy world, and what we can learn from them, and how these two exercises, simulation in the past and the future, are a bit quite different, but joined together. So I had based a lot of things on the screen, so let's see how this goes. I'll start with a short introduction to climate models, and really basically three parts of the climate of the past, an example of simulation, and the future. I just introduced that. So just to remind, with the risk of repeating what was said in the previous presentation, I'd like to show an example of the inside of a general climate model, which is in that case a general circulation models. So the concept of computational grid was explained before. So every box you see, there is defined temperature, moisture, various physical variables. The variables is a key word here. Then you have to make assumption of certain processes, how these variables relate to each other, and so basically the first principles are the conservation of energy, of moisture, and of momentum, motion, so Newton law, that kind of thing. So, and you can do that from box to box. So you have law that describes the heat exchange based on temperature between two neighboring boxes. If one is warm and the other is cold, there will be a heat transfer from the warm to the cold. Same with other quantities. And this describes every single equation and put them all together and to evolve to advance in the future. Every of these processes its own time scale, and that's enough for now to understand. Something else, you see that these different grid boxes represent different things. And the atmosphere on the top, the ocean lower left panel, you can see a bit of earth crust vegetation, different land types which have different properties. For example, different vegetation type will have different albedo, which is reflectivity of the sun radiation, which will have more or less permit more or less evaporation, absorb more or less moisture. Topography, the mountains will have an impact on the wind, and all these things are complete together. And these general circulation models have quite a bit of, the biggest one have many processes, and because they can have this relatively fine resolution, you don't have to parameterize too much. So parameterize is also another important word, that even though you start from a physical equation from first principle, which is really the specificity of physics compared to economy and all the fields, where all of this first principle, this equation, are kind of universals and works in a really broad range of situation and works. But when you arrive to numerical solution of these, you will have to make simplification somehow. If a grid box, it might be 100 kilometers, so you imagine some processes like clouds or thunderstorms and all the things are just not in there, you cannot, so they need to be parameterized. You will maybe think about, okay, what's missing? A storm, okay? What's the importance of it in what I'm interested in, the exchange of heat or that kind of thing. So if it's about the exchange, you will introduce maybe one term that adds additional exchange between two boxes based on some parameter that that will have this role, and which is more or less constrained from observation, but still that's your margin of freedom, the tunable aspect of model, which is always there, and the finest, the biggest the model may be less there. And the simpler you go, and more you have to play with these parameters, which is also a key aspect. So just a example of climate models here. This what you see is sea surface height above the zero reference level. On the left-hand side are satellite observations. So the reddish colors indicate height above 0, which may reach like 1 or 2 meters. Actually, well, you might not know, but sea level is not flat. Well, I won't expand too much into that. This will be another discussion, but well, the blue zones are a bit lower due to various reasons, which is salinity, more denser water, and wind, and Coriolis force, and other dynamic balance that can explain the slope. On the right-hand side is some climate models that represent the same thing. And I don't know if you can see, so well, but well, the broad features are just there, and well, not too bad represented. You have this height and the mid-latitudes, higher sea level, which underline the gyre circulation, which is ocean circulation around this height, and so they are. In all of this is not an exception. All of these big climate models do have these features. Maybe if you would zoom very detailed in a region, you won't have that. But broadly, they are really constrained by Earth rotation, mostly wind, where the sun, warmer temperature in the tropics, and so you have really many of these features. Even though you may play around with these parameters I mentioned, you would still get that unless you really do choose the crazy values which have no physical meaning. But you shouldn't do that, of course. Yeah, and here another example. I had a video for that, but it's, I remember when copying the file, I'm afraid it won't work. No, it won't. All right. Well, you would just see some points moving along from the middle to the sides, very slowly at the beginning and accelerating toward the edges, which is the model of the Antarctic ice sheets and representing surface velocity. So from process of snow accumulation in the middle and melting at the sides, well, you can derive low and represent the flow lines from a model, which you can also observe from observation. So these two examples I just meant, okay, you can be pretty close, really details and physical features. It's not, so climate models are more than, say, economic models, for example. They are not just calibration, just not statistic based on data and try, and project into the future based on that. The fact that they are based on first principles really give them particular legitimacy. Of course, there are many processes missing. For example, simulation of Antarctica for the first IPC we thought of, didn't have interaction at the ocean. Interaction with the ocean is a complex thing, involves many eddies, many motions at the edge, very fine resolution. It was just not there. So one of these IPC reports, projected in 2007, well, Antarctica will grow. Why? In a warming world. And the reason was that warming world also means moisture world, more moisture, so more precipitation, more snow, so growing. But just because they didn't include, just melting from the ocean, because the model were not able to do that yet. So you have to keep the two things in mind. Once, have processes that are based from something and just not taken from the air, but you still have control what you put in there, what you can. There are still all these choices, and there's always this question: do we have enough to represent what we are interested in simulating? And of course, you want to simulate sea level rise. Well, you'd better have the melting at the shelves, otherwise it's not very useful. That was one point. So I'll do more practical examples about ice ages, and here, well, you can, I don't know, it's in Alaska or somewhere like that, or Canada. Some lakes and sea which are of this rest in the landscape of the big ice sheets that were there 20,000 years ago, and removed, melted down, and the sea level was then 200 to 100 meters lower than nowadays, which is a lot. So Bering Strait was not only frozen, but just it was rocks, because it's only 60 meters deep, and all that kind of thing. So, well, but there are a few signs. You have the landscape, and there are people on America. So, well, they might be in a way together. So probably they went through Bering Strait. So many indications of through coral. So many proxies, observation. You have signs of these ice edges, but well, and the problem now is how to what really happened and how to understand that. And so there have been a theory, Milankovitch. Well, Milankovitch theory. Well, I wouldn't actually should have checked the date. I don't know. I think somewhere in the middle of the century came up with in the 60s, but I'm not sure where it came up with the idea that. Because these cycles, actually, if you look at the data, are cyclical and repeat itself, every 100,000 years or so. they must be related to some cyclical process and therefore to orbital parameters, like which is, here you can see the ellipse of the Earth around the Sun. This ellipse is not completely constant, it can oscillate, become more or less flat. The eccentricity, the rotation of Earth around its axis also changes a little bit, and all this has an influence mostly on, say, seasonal radiation, seasonal solar irradiation, how much sun shines in a specific region at a specific season. In that case, the Milankovitch theory was, the idea is like, what's important is northern hemisphere around Greenland, or where all the ice sheets are in summer. So around a certain time, it becomes very cold summer, so ice sheets start to have time to grow and can build up. It starts to snow, the ice builds up, and since there's more snow, higher elevation, it becomes also colder with the heights, and there's then feedbacks associated with the height of the ice sheet. It becomes colder and colder, so less and less melting overall. It accumulates and grows until it reaches the ocean or something, but otherwise it's like a constrained process. Well, there's still some issue with these theories. The termination of the ice cycles was sometimes abrupt and asymmetric. Also, CO2 is also changing. Why is CO2 changing at the same time? All that kind of thing. So yeah, a number of issues, and show how this very climate model, Climate 2, that you can see here, developed at the Potsdam Institute for Climate Impact Research, Andrzej Ganopolski. A very simple model because it has to go through ice cycles, so it's hundreds of thousands of years. You cannot do with the GCM, which is there only for 100 years. It's just too complex, computationally expensive. But that one is like, you see this maybe 10 degrees latitude box, 3 or basin for the ocean, 7 for the atmosphere. Very simple, but has enough features like the sun, energy exchange between tropics and the poles, and some mountains, a number of things, which is called Earth model of intermediate complexity. The idea is that it's simple, but have as many processes are needed, and just as many things as needed. And Professor just a very overview of all the things inside. So you have steam for all processes at the surface, evaporation thing, the ocean, some terrestrial vegetation, still inland ice, and in the ocean itself, you have all the cycles of chemistry and biology. So, I won't enter into the detail, but there are coarse resolution, but many processes. That's also a trade-off, that since you don't have to simulate so many cells, you can include more things without it to become too expensive. So you can have more things that actually in the big GCMs. And with that, Andrzej Ganopolski really was the first to really simulate the glacial cycles. So I'll spend a bit of time to explain this figure, and there are two more like that coming, so it's better if you get familiar with that. You can see, maybe something interesting is also the difference between, you have input forcings, and so input, output. So I mentioned the variables earlier, things that are simulated by the model, so temperature of different boxes and so on. But you also have things that are outside the model, so how much sun, how much do you warm up, that's the forcing. So, and here, the forcings, what you give to the model, how you feed it in, are these two lines in the simulation. On the very top is the summer insolation in the northern latitudes, which is really the sun. The maximum sun you get in summer around Greenland, say. And you see this varies over time. The scale here is in kilo years, so 800,000 years. So all this oscillation you see represent several ice cycles. So the peaks are like our period interglacials. The down here are just like Antarctic temperature, and the south, the down are colder temperature. Here Antarctic temperature, you see, go from 0 to -40. So that's the difference between really around present, the coldest place you may see, well, -40 is not that cold, I don't know what the unit. I would have said actually it's not as much. It's okay, I'll really pay attention. Thank you. Yeah. These scales, Antarctic temperature, I wouldn't trust it, but you still have oscillation of like 10 degrees between ice age and cold period and so on. So this model was just fed in with this maximum submarine insolation that you can reconstruct from data from orbital calculation, and at the second parameter from measured CO2 in ice, because you can say, you can measure in ice how much gas bubbles were there, how much CO2 was present at different times. So all over this window you see on the screen, these 100,000 of years, you actually have data just from analyzing ice cores. And these models, like looking at how much CO2 there is, you can reconstruct kind of a forcing, how much energy through greenhouse gases, how much energy will be applied, additional perturbation compared to present day will be applied to the model. And the output is in the lower panel, which is the global ice volume, the output in red, and the Antarctic temperature here in red also, which is superimposed to, the lower temperature, which is superimposed to measured data. So the black curve is this paleo data, and the red curve is the model. And you see a very close match, very, very close match. It was the first time it was so closely simulated. Well, notice not like entirely, say the CO2 and why CO2 cycle here is still not explained, just taken from the ice. Okay, we see CO2 varies, or the greenhouse gases varies by that much, so it must have this much of an influence, and that applied to in the model and see what happens. And well, they were able to measure ice volumes, therefore sea level rise and temperature in Antarctica in a convincing way. So yeah, this was quite an achievement. Well, here there will be another video. So on the top, you see the white thing moving is the ice sheet. It grows, and it's a fake map because the model doesn't have so much boxes. But you can see things moving around time here. It's really over every time point, every thousands of years. So it grows. There are several glacial cycles in there. So what happened here? You see ice sheet building up on the North America, or melting, building up on Scandinavia. This is cold ice, so ice time everywhere. I don't know if you can see something like so disappearing again. So, well, that kind of thing, output of the model, and of course feedback on when there's all these ice sheets, there's a lot of ice, it's very white, it reflects the sun, so it maintains a cool state. So, well, that's the kind of thing you can simulate. I'll come back to the presentation if I can. To what? Left.
Or maybe it's
play. All right, nice. So whatever. I'll skip. I don't have so much time, so I'll skip that. But just it was a process where slowly, the model still improved, and here you can, over the last glacial cycle, they build it up. They build it also a CO2 cycle model. So you see the curve here on the red, where CO2 is also simulated by the model with processes involving things like ocean absorption of the carbon, and because ocean becomes cooler, therefore absorb more CO2. There's less left in the atmosphere, therefore it makes it even cooler. Or things like iron phytoplankton, which do more photosynthesis, leading to more CO2 drawdown in the ocean. And why do they do more photosynthesis? Because they get more iron, which comes through Sahara dust, which itself, there's more Saharan dust in the air because the air is drier in a cold climate. All these kind of interlinkages where maybe you have to think about them first, maybe build them in a model in a reasonable ways and try and run it. Or other things like dust, sediments beneath the ice sheets, when they retreat and they erodates or do more dust, become dark deposition on the ice sheet, which makes them melt very fast at the end. All these kind of small things are in there, and you try and slowly, and when you get something like that, you can okay, I'm first happy. Okay, I am able to quantify some observed process in a very reasonable way. So it provides you with an explanation. Well, I'll come back to that in a second. Yeah, and the last version of the model, the only input was purely insolation here. It lasts glacial cycle, 107 years. the only forcing input was the curve, and the model was itself be able to reproduce all these complex pattern below or from the observation purely based on internal processes. Yeah, okay, I'll strike to that. So basically, to conclude on that, so in this model, he proposed a set of mechanisms involving force, so astronomical forcings, ice sheet, CO2, ocean, land, physical, biological processes, dust cycle, and the proposed plausible explanation for the ice cycles, quantitative, that work. If you can separate all of these processes, put a number, explain how you computed them and what you did, what assumption you make, and based on this assumption, you manage to reproduce reality. And that, because of all these many feedbacks, only models simulation can calculate that, and thought experiment is not enough. So is that convincing? Okay, this is a very coarse resolution of the model, many uncertain parameters involved, probably some tuning. If you have, in the first time you ran all that, you had a crazy outputs and nothing to do with reality. It's only after a process of trying to look at everything, change a bit this parameter, uncertain parameter, and that you end up at this result. So is it enough? Would you discard the model for that reason? I don't think so, because you can, all these parameters, of course, you have provided there's some trust involved in there, that probably the climate scientist who did that is honest, and I think he is, I know him a bit. You choose these parameters within bounds, so it's might be other explanation, but the really thing is you don't need to explain, to require black magic for all that. No, it's really, there's one plausible explanation based on things you understand. There might be other ones, but it's really a qualitative step to have this set of processes that may be the reason for that, even though there's a discussion continuing about how much exactly and all that. So yeah, what about the future? I'll try to speed up on that. So why should we trust the future? Because in the past, as I said, in the past you have some observation, you try to explain them, and you have a process of model tuning, evolution to reproduce that. In the future you have, well, no proof. So while you can say, all right, it's based on physical principles, so these physical principles are perpetual, so to say. But well, as I mentioned, of course, there's still this parameterization issue. So it's not completely that, but well, for the GCMs it's maybe less a problem. They can reproduce present climate or past climate. They are also validated, so to say. So this is something interesting. They can the robustness. It means okay, they all say the same thing, even if they were developed differently. It adds to confidence. It adds trust. Or processes. They are able to simulate so detailed things that it's impressive or interesting qualitatively, or possible things that may happen in the future. Like, for example, these four pictures show around Antarctica. Red is warm ocean water, and blue is the cold ocean water, and you have time slices. First in 2070, 2080, 2095, and you see this red tongue of water penetrating closer to the Antarctic ice sheet, which means a potential for melting. And such an intrusion of water, okay, you can say, and people said before, okay, there's a risk that this water come in, and we're observing ice sheets are already melting nowadays, and we measured warm water here. What is it? Maybe if this was more frequent in the future, this would be a big risk for Antarctic melting. So this guy come out with this model, a high-resolution ocean model in this particular region, and really in his simulation, he can see that with warming and oceanic processes, at some point, for some reason, water goes onto the shelf and get closer to the Antarctic. So in such a situation, okay, this means a lot of melting there and potential for retreat of the ice sheets. So at least it gives us a hint that, okay, physically it is possible that this happens, because I can show it. In my model, this happens. So it means it might happen in reality, and this is something we should consider. So this is interesting in processes. You have other ways of seeing the future. It's the idea of the ensemble of opportunities. You take many different models. Maybe in that case, Old means the last IPCC number 4 assessment. New is the newer one, came up last year. These different colors are different climate scenarios, and you know, and all of these shading and bands are made and it's kind of represent actually 20 different GCMs. So this is a way of dealing with uncertainty. You take them all and look the range they span, and at least gives you a bit of a feeling for you know, how much this range might be. Okay, maybe you don't span the whole range of possibilities because the models are not completely independent with each other. Maybe they share ocean component, they share something, but there are enough 20 different groups in the world, so at least you don't have to blindly trust one person. It gives you an idea. It's a maximum, minimum, and so you start having to deal with uncertainty and probabilities in a more general sense. Another thing that is developing is on the probabilistic projection using climate emulators. So it's getting closer to the application policies here, because I mean the problem of these climate models, the bigger one, GCMs, that you run it once, it takes several weeks for one scenario or more, a month, and okay, that's it. So you cannot play so much with it, you cannot change so many parameters, you cannot test it so much, and explore different scenarios. These climate emulators are a bit funny because they are not, they don't try to simulate completely the real world, although they have components of the real world. So you see the box in the bottom, the components, all of that are ocean boxes. There is like a northern hemisphere, southern hemisphere, and on top 4 boxes of the atmosphere. The northern hemisphere land, northern hemisphere ocean, southern hemisphere land, southern hemisphere ocean. So very, very basics, but with the end physical equation to describe the exchange between them of this very unrealistic world. But with these processes and with this tunable parameter, you can make this match any other existing bigger model. So you pick up any GCM and curve that has this basic physics inside, then there's always a set of parameters here with this smaller model that can reproduce its behavior across a wide range of emissions. So from that you can really say with one model that calibrates to all of these different, you can run lots of simulations and have things like really building a model more not to understand processes, but to make the linkages between our actions, like the scenario, the emissions we emit, so CO2 scenarios on the left box here, emissions, which is also maybe also probabilistic itself, many curves, to concentration, because there's also a carbon cycle inside itself, also tuned to bigger models. So from emission to concentration in the atmosphere to radiative forcing is this, I didn't mention that, it's just the additional energy to the Earth coming from greenhouse gases, and to eventual climate response, which will be temperature, and all that probabilistic. So you end up for every emission scenarios, path, a number of pathways of temperature warming in a probabilistic way. So that's with that you can say, okay, explore with this, well, just a normal projection here, red and blue, which shows well, 2 different scenarios, and in the center are higher probabilities, higher toward the edges are less likely events, and you can start to do interesting things that on this very complex figure here on the right. So let me tell a few words. I have to cut. Well, I have I think 3 more slides. So in that case, you can relate. So on the x-axis, every single cumulative emission pathway in terms of total amount of carbon you emitted in the atmosphere, and on the y-axis, a range of possible of warming by the end of the century for every single emission pathways. So you can start to ask questions like how much can we emit while still staying below certain degrees of warming with a certain probability, and this kind of thing. Well, then you still have to decide what climate target you have to, you want to reach based on other external things like, okay, there's a study from Urbanson told that Greenland after more than 2 degrees warming, will melt down eventually. and that and all the lines of evidence convince and push politicians to agree on this 2-degree target in Copenhagen, and also because then it's also a political step. You know, you may say 2 degree, why 2 degree, not 1.5 and 2.5, and it's based on some simulations. It's okay, can maybe support it, but you know, maybe also different. It's also for politics, you also need really your climate goals to agree on it, and you know, to go somewhere. If you always question, I mean, this 2-degree target was based on model simulation, but then it's important for the climate process itself to have this target. Yeah, okay, then I'll stop. I won't talk about an example how science can inform and influence politics. Here, these climate action trackers. So these people just look at the pledges made by the countries, how much they will emit, how much they promise to reduce their emissions, and compared to the 2-degree targets. And simultaneously, with this simulator I introduced, they can compute temperature projection and see, okay, is it responsible to do that or not, and update that, and inform the talks, and during the negotiation themselves, to put into perspective the arguments, the pledges about the countries. So yeah, I'll stop for that. So basically what I mentioned, that there are very different kinds of models with their own domains of applications. Okay, you can, with study of past climate, you can regain understanding and process, we say the more scientific part of it. You can, well, projecting future climate is of course more delicate. It can only be quantified by model simulation, but there's no observation to validate, of course. So why should we trust them or not? This kind of question. I mean, of course, you have the physical equation that remains, but you need to deal with uncertainty and the idea of ensemble of opportunities or probabilistic statement about the future. To have to accept uncertainty to make decisions based on that, you will never be able to reduce that. Yeah, and then you can, with the link between cumulative CO2 emission and climate impacts, you can. It's useful to set policy target in terms of emissions, because there's also the aim, of course, to have this whole chain from emission to impact. Yeah, okay, that's it. That was it. So thank you for your attention. Sorry that I took a bit longer.